So yeah, go ahead. Let me know what your questions are.
Yeah, so you're the CEO of Stone Aerospace. What kind of company is it in terms of size? How many people do work under your command?
Yeah, we've got roughly 20 full-timers here at the Austin lab and 35 people who are what you might call remote workers. So we've been doing remote work for 20 years, ever since I established the lab down here. It was easier to have experts who didn't want to move, their job at the time, and so they do their work wherever they want. And when it's time to do something like system integration or a hardware, in the loop check, they'll fly down here. They'll spend a week or two at the lab, get their data, and then go home. So all over, we're roughly 45 people right now.
Okay, and what sort of annual budget do you operate on?
Oh, it varies. It's between 5 and 10 million a year is what we're pulling in.
All right, so that's from NASA contracts and.
Oh no, we do all kinds of things.
Okay.
Right now we're commercializing our sunfish vehicle. We spun off a new company called Sunfish Inc. And so that is now seeing commercial inspection operations where we send a team out with vehicles. They'll go and they'll do an underwater inspection of whatever you want, whether it's an aqueduct or a civil structure like a dam or a bridge, something like that, or if it's offshore power, whether it's wind power or oil and gas. And we take the vehicle out and we'll build a 3D model, analyze for damage, and give that kind of information to the contractor. So that's a direct commercial spin-off of all the 20 years worth of work that we did for NASA.
All right, yeah. So to get to the main topic here, let's assume we have a lander on Europa, and now we have to get under the ice. To do so, you need a melt probe, what you call a cryobot. And you have described two different approaches to building a cryobot: a laser approach with the Archimedes program, and a closed loop hot water approach with the TOR program. Could you briefly describe what those programs are?
Yeah, sure. There's actually an intermediate version that you missed there, which is a passive thermal probe.
Okay.
And that was one of the original designs that came out of the 1960s with Filbert up in Greenland. And there were a lot of people who thought that would never work. And one of the things that we've done here in the last 3 years is built what currently is the only outer planet simulator for cryobot ice penetration. It's a meter diameter, 2.5 meter tall slug of ice that's at 80 Kelvin and hard vacuum. And to cut to the chase, all three of those techniques will work. What you find is that they sublimate the ice off at the beginning, and as they get about 2 to 3 vehicle lengths below the surface, the hole will freeze back up. The sublimated ice will freeze back into the hole, close the hole shut, and you'll get vapor pressure, which will allow liquid water to form. So it works. I mean, there's no magical showstopper. A lot of people used to tell us you could never pull this mission off because of that problem. It was called the starting problem, and there was some German data that suggested that the radiative heat loss would simply form a crater, and the vehicle would just sit there, never going down. That's not the case. I can show you videos from multiple tests that have gone on. But to go back to your question, so we've been playing this game for a long time, and we've looked into a whole number of different technologies. The laser approach, there were actually 2 different versions. The original one was that we used optical power to create heat. So we expanded a high power industrial laser into a beam dump, absorbed the heat, ran that through a heat exchanger, and then we had a hot water jetting system that used that heat to melt the ice ahead of the vehicle. That was called Valkyrie. And we actually physically tested that out on the Matanuska Glacier, both in 2014 and 2015, and it works. How high power can you go? Well, right now you can buy an industrial 200 kilowatt laser. We were using simply a small helicopter portable 5 kilowatt unit, but it works. So it's just a matter of, how much speed do you want and how much power. So the one thing to remember is that when you're transferring optical power, you have to have a waveguide to do that. So the vehicle deploys a fiber optic link. It's a special custom design. It's not a telecom fiber. It's designed for high power transmission. And so we experimented in 2016 with the idea of using the optical power itself to see if we could melt ice, and surprisingly, nobody had actually ever done it. So we built a focusing lens system at the front of the vehicle, and the focal point was about 20 vehicle diameters ahead of the nose of the Cryobot. And what we discovered was that it was 100% efficient in transmitting the energy into the ice. And we set a, if you're into these kind of niche records, we set a Cryobot speed record of 22.5 meters per hour.
So that's the laser saber.
Yeah. And so it works. And when I showed that to the second Ocean Worlds workshop at Woods Hole back in 2016, it really opened a lot of minds to thinking that kind of mission was possible. But here's the limiting factor on that, is that the optical waveguide can only be so long, and once you get beyond a couple of kilometers, the attenuation in the fiber is enough that you're not getting enough to the vehicle when it slows down. So for an intermediate range mission, let's say you wanted to go a kilometer or even 2 kilometers in Mars, on the ice caps of Mars, this would be a great idea. As long as you don't hit any kind of heavy sediment or obstacles along the way. That is a limitation of this device. You have to have relatively clean ice. It doesn't mean you have to have pure ice. You can have salts, you can have hydrates, you can have acids, whatever you want, sulfur, as long as it's only a certain amount of percent, like less than about 10% of the ice. It'll go through that. And we've actually done that. We've put these things in the test chamber at Europa temperatures, and they go through it. So that's one. So if you wanted to do short range testing, the optical approach is good. The secondary one, the passive thermal probe, it's inefficient. It won't work with an optical system. Well, it will work with an optical system, but it's a dumb way to do it. The better way is to use a radiothermal source or a nuclear reactor. Once you leave the laser domain, you're into nuclear power. There's no way to escape this.
So the Cryobot uses the heat from the nuclear reactor instead of using the nuclear reactor to.
That's right. Yeah, and there are several groups right now that are looking at alternative designs for cryobots. One of them is kind of fixated on the use of radiothermal isotopes like plutonium-238. The problem there is that unless you change what has been a heritage design, it's what's on Mars right now, right? It's what is powering Curiosity, what is powering Perseverance. Those heat units are inefficient. They're designed for carrying it for power conversion, not for melting ice. So unless there was a whatever you want to call it, a release of standard protocol and repackaging of that material, you can't get enough of it in a small enough place to effectively melt the ice, and it will stall out. In fact, there are papers that show that this is in fact the case. The other problem is that when you look at what the minimum power requirements are, you find yourself at no less than 7 to 10 kilowatts worth of thermal power. And the problem there is that what are you going to do with that? Because a radiothermal isotope is on, from the second that they put that material in the launch vehicle, it is heating that vehicle. And 10 kilowatts is not an inconsequential amount of thermal heat. So you have to think, what are the implications of that throughout the entire transit phase? Going to Europa, and we came to the conclusion that it's not such a great idea, that there's a much better way to do it with a micro fission reactor. And so we actually designed both types. We did a 25 kilowatt radioisotope design, and we did a 100 kilowatt fission design. And the interesting thing about that is that the size of both of those came out very similar, about 16 centimeters in diameter and 75 centimeters long. This
so
is
it
not
would fit, yeah, it would fit inside a cryobot, no problem.
Yeah. And in fact, we have designed our current vehicles to emulate the presence of that reactor. So in other words, we have a surrogate power source that produces heat in the volume of that reactor, and then we do everything else around that as if the mission had a nuclear reactor.
Okay.
But if you're going to talk about going through 24 kilometers of ice, which is what the current thinking is for Europa, go back and read the latest papers by Papalardo and Howell. Excuse me a second there. And you'll find out that the current thinking is about 24 kilometers plus or minus 2 or 3 for Europa. Enceladus, they don't have really quite the data they need to do those calculations. But so 24 kilometers, of which about 20% is at the critical, cryogenic temperature, 80 Kelvin, and then gradually moving up to what people refer to as warm ice. Something that would be warmer than minus 30 centigrade. And then you got to get through all that. Well, it turns out that even with a 100 kilowatt reactor, you're looking at about 10 months worth of power. So to get through a Europa ice cap, you're talking about megawatt days of power. We're not talking about watts or kilowatts. It's megawatt days are the numbers that you're talking about to get through there. So the way to do it is a small nuclear fission reactor, and you can do that today with techniques where you sinter what's referred to as low enriched uranium, or even slightly greater enriched uranium, out to about 15%. This is not bomb grade material. This is like a nuclear power reactor material. So you can, a private company can build these things, and you can.
In terms of testing, how does it work? Because I'm sure there are a lot of regulations involved. So is it something that you can test your designs, or? Yes.
Oh yeah, absolutely. So you can build the thing. It's better to hot fire them though in a facility that's designed to do that. So they have them out at Nevada, they have them at Los Alamos and other things. And that's in fact where they did the testing of the kilopower reactor. That was the crusty experiment that you mentioned, right? So these things are doable. Those designs were more complicated than the one that we have come up with, which is a tungsten cermet material, in which the uranium is sintered in with the tungsten, and then you have a single boron control rod that comes down the middle, and then around that you have thermal converter chips that generate the electrical power. A lot of people have talked about using different heat cycle engines to do this, but the problem is moving parts can break, especially on a long duration mission. You're talking on the order of 6 to 8 years to run this mission. So you have to have something that's going to be simple and reliable. And so that really boils down to solid state power conversion.
And so in its current design, this is something that could work on Europa. You mentioned something like 10 months to reach the ocean. Is this a reasonable timeline, or this is to develop something more powerful?
No.
Okay.
100 kilowatts is plenty to get through Europa, and the good news is it will fit within what we consider to be a flight mission compatible cryobot. So you mentioned the Thor vehicle. So that is a full closed cycle hot water drill system, which has a core that emulates a 100 kilowatt fission reactor. And the way we do that is we have a exterior 10 kilowatt or 10,000 volt rather power system. So it's very high voltage. And that goes down as AC power to a liquid resistor that is the size of the nuclear reactor. And so we can convert 600 kilowatts in a liter volume in the vehicle using this. We've proven these metrics. And so then from that, we pull in water from the melt in front of the vehicle. It goes through a heat exchanger that cycles with this liquid resistor. And so you can dump enormous amounts of power. This was the big problem with the old Filbert probes, for example, is that when they tried to put electrical power into the vehicle, they burned up the resistors. You couldn't get resistors that had big enough area to handle the power. Well, we solved that by going to this liquid resistor approach. And so now, we can make this vehicle run anywhere on Earth that we want, using this alternative power system. The problem is they're not going to let us put a nuke in Antarctica or Greenland, right? So we have to prove it this way, and then eventually there'll be some larger scale chamber testing with an actual power system in it. But this is proving everything out that needs to happen.
And Thor is basically the size of what we could send to Europa, at least in terms of diameter, as I understand it. It would need to be a little bit taller, right?
Thor was sized to carry a kilopower reactor, upgraded to 100 kilowatts. And so that's how we ended up with 35 centimeters. The length right now is about 2.5 meters, but that does not include the science payload or any of the vertical motion control systems that have to go in to prevent loss of the vehicle if you hit a void or when you hit the ocean interface.
So it could be double that or something like
that. It'll probably be on the order of 5 meters long, possibly even as much as 6. It's one of these things where you're fighting the physics, because
that's what I was going to say is increasing the length.
So if you really want to dig into the nitty gritty, go back and look up something called the AMOT equation, which will give you the power distribution around an object that's penetrating ice. And so it turns out that depending on the temperature of the ice and all that kind of stuff, the diameter of the vehicle and the length of the vehicle come into two different aspects of the speed calculation. The speed is inversely proportional to the diameter of the vehicle, right? So if I double the diameter of the vehicle, I slow down by a factor of 4, right, with the same power requirement. So, if you want to get down at any reasonable time, you have to keep the vehicle small in diameter. Well, the problem then is you have all these systems, they got to go somewhere, right? Well, the vehicle just keeps getting taller and taller and taller. Well, there's a problem, okay? And that is that if you look at this AMOT equation, you see this curve, right, where the power that is needed along the length of the vehicle to keep it from refreezing into the hole, right, goes up over length, right? So you could end up spending 90% of your power just keeping the back end of the vehicle from refreezing, right? So there's this optimum number, and we've come up with an aspect ratio of 15:1. So 15 diameters as the length of the vehicle it's kind of an optimum number for outer planet designs. And so right now, for an initial mission to the European Ocean, we're looking at, a 35 centimeter vehicle, maybe as much as 40 centimeters, with a 100 kilowatt nuclear core, and anywhere from 5 to 6 meters long. I think this is a reasonable bound of what's going to happen in reality. When you could try to make it smaller. Okay, you could try to play these little tricks. You could use radiothermal sources instead of a fission reactor, but I think it's a mistake if you do that. The beauty of the fission reactor source and the closed cycle hot water jet is that if you do run into something, you can back up and vector the jet to allow you to move. Okay, and we proved that with Valkyrie. We actually had a 7-degree off-axis deviation with the vehicle by using lateral cutting jets. So it works. And the other good news there is that you can use those jets to create a pocket if the vehicle has stopped. Usually you're not going to hit a house-sized rock. What you're going to do is you're going to hit some gravel, maybe a little deposit here or there from a meteorite impact or something like that. Well, if you create a pocket to the side and then use the jets to randomly move the debris out of the way, it will keep going down. And we also showed that you could do that with Valkyrie. So Thor is a much more high power system than Valkyrie ever was. The pressures are much higher, the temperatures are much higher, the flow rates are much higher. It's designed to be an industrial strength machine to go through 4 kilometers of Antarctic ice cap as a demonstration, and then a carrier vehicle for testing all the other advanced types of systems that you want to do for these outer planet missions.
And how is testing going right now? I saw you mention going to Iceland and going through a glacier, and
that's phase 2. that's phase two. Right now, we're finishing up phase one. We have a lot of data that we've got to publish and things like that.
Right.
And then, depending on the whims of NASA funding cycles, phase two could start as early as next year, or it might be a 12-month or something like that hiatus until they get their cycles aligned. But the fact is, the vehicle works. We did a 4-day, 50 kilowatt full power test, and it runs. So what we need to do next is take it out and do the glacier penetration to show that it's working there. And then the next phase beyond that is to start adding back in the science payloads to do all the life search. And I don't know how much of that you're interested in or paying attention to, but there's a lot of activity going on right now in how you go about detecting life. And and by that I mean unicellular and multicellular small life form, 200 micron size critters. Nobody at NASA headquarters, and probably ESA as well, is thinking that they're going to see a fish swim by on Europa. If you did, well, that's end game. You don't have to go through any of these complicated life detection and verification. It's like, there it is. Okay, that's a win for the team. I don't think that's going to happen. There are other people who wishfully think that it might happen. I don't think there's enough energy on Europa to do that. But what I do think, and this is in discussions with a lot of astrobiologists, that's one of the benefits of doing the kind of work that we do, is that you have to put multidisciplinary teams together. And so I have a half dozen or 8 molecular biologists and microbiologists that we work with regularly. And so I'm very, very knowledgeable of what is happening in those fields. And so it's a situation where a lot of people now are beginning to think that there's a whole class of bacteria, which might be called nanobacteria, that are in the sub-micron range, like sub-tenth of a micron range, that are far more ubiquitous in extremophile environments. These would be very low energy environments. These would be chemoautotrophic organisms. But the fact that they exist at those extremes suggests that they may be ubiquitous in a low energy ocean, not necessarily grouped around a hydrothermal vent. Although the idea of a hydrothermal vent is a realistic estimate in my mind of what might be found on the floor of the European Ocean. So my point of that is that if you work on the detection and the validation of a nanobacteria discovery in the open water column, you may not need to go much more than breaking through into the ocean to find that, or you may even see it in the ice column because the ice is accreting underneath and ablating on the surface. I don't know if you're familiar with this phenomenon. I've seen it personally in Antarctica, where a very strange phenomenon happened. For example, you can get what's called basal ice on the floor of the Ross Sea that will ice in a sponge. And then when the ice accretes on the sponge, it becomes positively buoyant. The sponge will rise up to the bottom of the ice cap. And then as the surface ablates, the bottom accretes and the sponge keeps moving upwards until eventually you have sponges on the surface of the ice cap. And you're going, how the heck did that get there? Right? Well, there are people who believe that might happen in the European ice cap. And so while you are going down, we have actually done probably more than anybody else, the development of in-vehicle triage sensors. Okay, and the classic one that we've been using is a deep ultraviolet flow spectrometer. It's an instrument called SURFs, and I could give you a long lecture on about the other 10 instruments in the detection chain that are important. But the interesting thing about SURFs is that it's continuously functioning, so you can use it as a triage instrument for the duration of the mission. And what happens is, if any type of biological material, could be a biomarker, could be a piece of something, a polyaromatic hydrocarbon, an amino acid, not necessarily even life itself, but, things that would suggest that there might be life hanging around. Well, when you hit those things with a range of frequencies down in the deep ultraviolet, they will glow, they'll fluoresce. And so if you have a single photon detector on the other side of that, you can build a spectroscopy chart of magnitude versus wavelength, right? And then you can go through that and go, that is an amino acid, that is a polyaromatic hydrocarbon, that right there is a protein, right? And from that, you would say, wait a minute, there's something funny going on here. Maybe I should send this sample up to more sophisticated instruments. And right now we've been working with field versions of DNA sequencers. I'm sure you've probably heard of these things. Well, we're working to actually integrate them into the vehicle itself.
Yeah, that was going to be my question. Do these instruments currently fit inside of the Cryobot, or is it still?
Yeah, the short answer is not quite. But what is happening right now, there is work to develop microfluidic front ends for the sequencers. The sequencers themselves are small enough to fit in the Cryobot, but there's a problem. The problem is that it uses consumables that are usually, at least right now, administered by human scientists. Right. So two things come up there. One is you have to replace the scientist, and the second thing is these consumables are limited. You can't carry an unlimited supply of them. So you might have, let's say, 10 shots, 10 tries you get. So how do you make the decision as to what sample gets sent up to use one of your precious 10 tries? Because if you use them all up, right, and then the 11th one is the one that actually had life, well, you just wasted a $4 billion mission, right? So you get into all these interesting software decision making algorithms, and the simplest one that people may have heard of is called the secretary algorithm, and you can go on. There's much more sophisticated versions, and we've implemented all of them. We had the secretary algorithm in 2014 running on Valkyrie, and we actually beat the guesses of the field microbiologists who were there in interpreting the data. It's pointing the direction that things will work, where we can build an autonomous life detection system that will fit onto one of these vehicles. But going back just to one thing to make sure you understand this, the current thinking is that nobody knows what exists even in the ice cap or even further away, the potential ocean. And so you would not go doing something like attempting to put an autonomous underwater vehicle on the first mission that goes into the ice cap. It's going to be a pure Cryobot mission. You have to have a way to control the vertical position of the Cryobot, because if it falls into a void, it could actually be a vacuum void because of a seismic crack up in the brittle ice. Nobody really knows how active the surface of Europa is. There are conjectures that there are cryoseismic events, but nobody knows this. Right?
Until we can.
It could have been 10 million years ago that all those cracks formed on Europa. There's really nobody's been there. Nobody's sit there going, hey, I've got a seismometer, they're happening every hour, they're happening every 1,000 hours or whatever. But there's people who say, well, it's a risk. It might happen, right? And so if it did happen, a couple of problems could happen. Your vehicle might fall into a vacuum void. It could fall into an intermediate level lake that some people have hypothesized from convection, heating over thousands of years. Or for certain, when you hit the ocean interface, if you don't have a way to control its vertical position, you're in trouble. It just drops off, and that's it, end of mission. So what we really want to do is get to the ocean and drop the vehicle all the way to the floor in a controlled fashion for several reasons. Number one, we don't know what the chemistry is. We don't know what the temperature variation is. We don't know what the current situation is. Do those vary with the tidal cycles of an orbit around Jupiter, right? Are they, several tens of, meters per second in terms of flow? Are they low flow? Nobody knows. And all of that.
So that would be the Cryobot descending tethered by optic fiber or something like that?
Not an optical fiber. We want to carry an optical fiber, but no, it would probably be more like a Dyneema or a Spectra micro tether.
Okay.
That the vehicle spools out. But the idea then is to send it all the way to the floor.
Around 100 kilometers or something.
That's the maximum numbers we've heard. Could be as low as 30 to 40 to 50.
Okay.
But somewhere in that range. Go all the way to the floor, and then take whatever data you can get at that point. We've actually had people suggesting that we use the control system to allow currents to pendulum swing the vehicle so that you can cover terrain. That the more terrain you can see, the better, because the likelihood of you landing straight on top of a hydrothermal vent is about zero, right?
Sure.
Right. Which is the argument for having an AUV, because then you increase the radius of exploration from the point. But I've totally come to the conclusion that any successful mission will involve going to the floor, not the underside of the ice cap. And then from the floor, you can expand outward with an autonomous vehicle, building maps as you go so that you know how to get back, and then you uplink your data. So it's a very bold mission, as you're aware.
Absolutely, yeah. So the Cryobot would need to withstand the pressure at the bottom of the ocean.
That's right. Yeah, and the maximum numbers we've seen is about 1.6 times the depth of the Challenger Deep here on Earth, and those are within engineering design parameters. We can design for that.
Okay, and could it have a camera or something like that?
I'm sorry, a what?
A camera?
Oh, of course. I mean, if you go back and look at any of our vehicles, like Artemis, for example, was a scientific Christmas tree. It had over 100 instruments. We had 5 different HD cameras on that vehicle.
All right,
yeah. I mean, all of that will be in there. Currently, Thor carries 3 cameras.
Okay.
And that's your primary science instrument. Everything else, is supporting material that gives you environmental data, that gives you, possible chemistry and things of that nature. So typically, right now, the sensors that we have are water chemistry. So these are the classic, water chemistry, like conductivity, temperature, depth, right? So you have a deep ultraviolet flow spectrometer. You can have basically wet chemistry electrodes that do ion specific characteristics of the water. So those are your kind of like your 3 normal ones. Then when you get above that, you're into things like chirality sensing of potential biological material or origin being biological, right? You're into things like 3D holographic microscopes that would look at motion, shape, texture, things of that nature. Right now, people are working on libraries of microbial characteristics. And so by the time this mission comes about, that database will probably be loaded in memory of the vehicle, so that you can do archetype comparisons between what you see in your machine vision camera versus what you have in your library. I mean, as you probably...
Is that something that can be done with current tech with AI? Because obviously you can do that remotely. So is this something that's currently...
It all has to be done on the vehicle. There will be nothing that will be sent. Nothing sent back to Earth. This is so far beyond what is happening on Mars right now. That is basically what you would refer to in robotics as a scripted mission, right? 50 people at Jet Propulsion Laboratory write out a piece of code every day that says, turn to 320 degrees, move 1.25 meters, stop, rotate, right? You get it, right? Scripted choreography. That's not the way any of our vehicles work.
Absolutely.
They're all behavior based, right? So you give them broad global goals, and then they have to make the decisions on what to do.
And this is not sci-fi. That's currently what they're doing, right?
That's what. Well, so the Mars rovers are doing scripted missions.
No, I know, but your vehicles are currently...
so Sunfish is completely AI. It's all behavior based. We will typically say, a mission description that we upload to the vehicle is, we want you to explore, number 1. Number 2, we don't want you to get any closer than 10 meters to an obstacle. Number 3, we want you to go as far north as you possibly can. And number 4, we don't want you to violate the following depth restriction or the following power minimum requirements. And that's it. 5 lines of code, and the vehicle goes off and explores. If you have not seen it yet, type in sunfish Namibia.
Yeah, I've seen the video. It's great. I mean, you should definitely do more of that type of.
But we're doing plenty of that. We have 3
Yeah.
years worth of funded work from multiple sponsors right now in that area.
That's great.
So things are moving rapidly, and that's beyond the level of the Cryobot work.
Sure.
It's really, if NASA is funding the mission, that's 30 to 40 years out in the future. If we get a private sponsor, we might be able to launch a Cryobot mission in under 7 years.
Yeah, that's amazing. I'm just thinking back about the nuclear reactor. What would be the per unit cost of one of your design?
Yeah, we actually worked that out for 100 kilowatt fission reactor.
Yeah.
You're looking at about $12 to $15 million.
Yeah,
that yeah.
I mean, an MMRTG is like 100 million.
Well, so there's a reason for that, okay, and you have to understand the nature of the.
I'm guessing.
Well, yes, you hit it, but you have to understand why, okay. Plutonium-238 is the desired radiothermal source for a lot of reasons. It's a nice pure alpha emitter. It's got very good thermal characteristics. You get watts per gram, right? It's easy to shield. And then you simply put a static, tech converter system around that to get your electrical power, and it's very, very reliable. The problem is that to produce plutonium-238 right now, the standard method for doing that is by irradiation of certain radioisotopes in a nuclear reactor, allowing those to decay and then doing chemical separation. Well, the prices that the Department of Energy, gives NASA are astronomical, right? Hundreds and hundreds of $1 million just to get a kilogram of material. And for the Martian rovers right now, I think it's 2 kilograms per rover, right? Yeah. And so that is the problem. There are some people that I'm aware of that are looking at alternative commercial means to produce plutonium-238, largely to enable commercial deep space missions.
That's what I was going to ask. Have you thought about commercializing your nuclear reactor as a propulsion or power source for?
So here's the thing. When you talk about nuclear thermal propulsion, you're not talking 100 kilowatts. You're talking megawatts. Okay. So these are much bigger reactors, and there are funded programs right now that are looking at developing those. We're not competing in that arena. Okay. The area of small scale RTGs based on alternative materials to plutonium-238, we are working in that area. And we are working in the small 50 to 100 kilowatt reactor range for the propulsion or for the melting of cryobots, right? But the small scale RTG work that we're doing looks like it will be sufficient for most of the other things that we want to do. Okay. So, there's interesting possibilities on the horizon where we don't have to wait for cheap plutonium-238 if we want to launch a mission. So if a billionaire came to me tomorrow and said, "Hey, let's go to Europa," I would give him about a 7-year time to launch to get everything in. And that would give us about 3 years beyond the expected certification and licensing times to get these things approved for launch. Right? It does take time. But the good news is there's no black magic involved. There's no legal, hurdles to get over. You just simply have to go through the paperwork. Okay. And build it and show that you've done what they expect you to do. So we know how to do that. We know how much it costs, and it's just a question of does somebody want to put the money on the table and go ahead and do the mission?
And so the RTG work you mentioned, what would that be used for?
You can use it for powering all the instruments on board.
Okay, so the nuclear reactor only powers the melting part. So
the thermal source. Yeah.
Okay. All right.
Yeah.
And what's the cost of an RTG with your design?
That would surprisingly, it would end up being very close, about 10 million. And the reason is you have to refine the material and then put it into containers that are radiation safe.
This one is not using plutonium; it's the strontium-90, right?
That's correct. Okay, yeah.
That's much cheaper, I'm guessing.
Much cheaper, but it does have the problem that one of its decay products has a decay cycle that occasionally involves a gamma
Okay. Yeah.
response. So you have to shield against that if you're going to be having this being used by humans, or I'm going to handle this and put it in my Cryobot. Well, then you have to have an additional shielding requirement to do that. So, we're working all that. It's doable. There's nothing in there that's a showstopper.
And so one RTG would power all the instruments of the Cryobot.
That's right. Yeah, for about 15 years.
That's great. And could you test like the TOR program on Lake Vostok or another Antarctic?
Absolutely. We want to do something a little bit simpler first. That was why Iceland was targeted.
Sure. Yeah.
And so that's only about 300 meters worth of ice cap there. And it does open out into, there's a couple places where there are subglacial lakes. Yeah. And so that's the initial target for phase 2 of Thor. And once we do that and show that all of the elements are reliable under sustained power, then the very next thing would be to go to some of the Antarctic subglacial lakes, which, as you're aware, reach depths of 4,000 meters.
Yeah.
So Vostok is one of those, but I can tell you, having talked to the scientific community, there's about 300 other sites that people are very interested in. Some of them are far more interesting than Vostok.
Okay, I'm guessing that's a logistical nightmare to put something like this on the surface of Antarctica and
Actually not.
No?
Actually not. No, if you go and look at some of the recent work in the last 7 years that, for example, the National Science Foundation has funded the Wizard project, the Salsa project, and a couple of projects done by New Zealanders with smaller drills. But these were hot water drills that produced holes that were very similar to what Thor would produce. And the problem they had is that to put those in the field was 500 metric tons of equipment, right? That's a lot of gear. It's a tour de force. Those were $50 million projects to put one hole in the ground through 700 meters of ice. Thor is a much more mobile system than any of those places. And part of the reason that it really excels is that when you go back and look at, for example, the Wizard project, all of that work, all of those years of planning and the fielding of that team produced one hole that froze back shut within 36 hours. If they wanted to stay longer, they had to ream the hole and then they'd get another 24 hours. But they weren't on site more than a couple of days with the hole actually in use. The thing about Thor is that it's bidirectional. Okay. So it doesn't care that the hole is going to freeze behind it. It just keeps on going down, does its mission, and when you're ready to come home, you reverse the cutting jets on the hot water drill, and you pull yourself back to the surface.
But to test it, you would need to have a sort of permanent base on Antarctica to.
Yeah, well, we have one. It's called South Pole Station.
I know, but the subglacial lakes that you would want to reach up, I'm guessing.
So
directly above it. So
a couple things you might not be aware of. Most of these places are accessible both by C-130 aircraft, cargo aircraft, as well as by something called the South Pole Overland Traverse. This is where they use tractors to tow sleds. It's how South Pole Station is mainly supplied, is by the supply train that comes using tractors to haul 3 or 4 14-meter long sleds of heavy equipment to South Pole, including fuel and things like that. So those approaches are available, but it makes sense to do some of the initial work near some of the established stations. So Vostok, Casey Station, US South Pole Station, all of those would be good places to base some initial work from. And there's actually a lot of data around South Pole Station from the IceCube project, where they drilled up to 100 holes to put these neutrino scintillators in the ice, right? So we know what the ice characteristics are, the temperatures. We can tell you pretty much how long it's going to take Thor to get through based on the power and the ice temperature profile. So the nice thing is we don't have any heavy equipment that goes with this. Once you have a portable carbon tripod that lifts the vehicle up. Once it gets into the ground, it goes by itself. It doesn't need any other, big hoses. Look at the Ice Cube project. They have a hot water drill hose that has to be the size of a house, on a gigantic drum that might be 10 meters in diameter and 25 meters long that carries all the hose that has to run the hot water down that drill. We get away with all that. We don't have any of that. We don't have any of the burners that they have and things like that. It uses a diesel generator to provide the power, but that's it.
So you can just leave it and do its thing.
Yeah. We just have to have a depot of diesel fuel to run the generator. Okay. But otherwise, the surface infrastructure is pretty much whatever you want in terms of a small human crew to just make sure it's functioning and repair anything that goes wrong if the generator shuts down or something like that. So the footprint of this is probably on the order of a 50th of what the Wizard drill was, to do more.
Sure. Yeah. So when you reach a lake on Earth or an ocean on Europa, obviously you need a cryobot that is going to be extremely clean. So could it be sterilized to an acceptable level of planetary protection?
That's the whole idea. The beauty of a cryobot is that it is a self-contained device.
So you can heat it.
You can heat it. You can clean it with hydrogen peroxide. You can put it into a sterile wrapper that you then take down. Even if you want to do this in Antarctica, right? You can do it this way, so that when you put it into the ice, it is as clean as it will be on a planetary mission. And there have been very interesting experiments conducted by Joe McCookie and some people up at University of Washington, where they tracked the propagation of microbes from the surface behind a passive thermal probe. And what they discovered was that after a few vehicle lengths, any surface-based microbes were gone. So basically, you're not transporting anything down with you. And as long as the vehicle is sterile when it goes in, you're not going to be affecting the life through the ice as you go.
Well, that's good to know, because that's a major issue, of course, on a mission like this.
Yeah. Right. But if you're talking about a life search mission on Europa, what you have to do, the gold standard, is to detect something that is not matching any DNA sequence on Earth.
Absolutely.
Right. That's the gold standard. So if you have, 1,000 base pairs that are not like anything ever seen on Earth, that's going to be it, regardless of what it looks like. But if you say, hey, this 1,000 base pair sequence is E. coli, well, then somebody in Jet Propulsion Laboratories or somewhere else
didn't wash their hands.
Didn't wash their hands and touched it after it had been sterilized. Right. And so that's the and I don't know how familiar you are with planetary protection standards, but they are not 100%.
Yeah, I know.
Okay?
Yeah.
You will never get the cleanliness down to a level of less than perhaps 100 microbes per square meter. It's not going to be zero.
Sure.
Ever.
Absolutely. Yeah. And so you mentioned finding a billionaire that can fund a mission to Europa. I think you mentioned in previous interviews a price tag of something like 1.5 or $2 billion.
Less, I think is yeah.
Could you break that down? The cost of the launch, the lander, and
yeah. So the reason I'm saying less is largely because of SpaceX. Okay. Yeah. So you have a couple of things that have to happen. Number one is, to get something out there, you need a fairly big launch vehicle. Okay, so everybody has assumed, up until recently, that was going to be the SLS launch system. Okay, and if you pay attention to the news, even if you're kind of not very educated, you're going to get the idea that this is a political game with that vehicle. It's a jobs program. Okay,
it's not going to fly very often.
No, in fact, they've just again now said that returning to the moon will be many years off now. You know, it used to be they were going to be there by 2024. Well, then it used to be it was 2020, then it was 2015, then it was 2000. You know, it's a rolling target that's about 20 years in the future always.
Right.
Right. So but there's a way around this. Okay, there's a way around this. And if you see what is happening right now with the resupply of the International Space Station. Yep. These are automated cargo vessels, right, that go up and will dock. And I can tell you a lot about that because we use these same concepts with Sunfish. Sunfish and Artemis were all auto docking vehicles. Artemis, in fact, came in using 3-stage navigation from as much as 10 kilometers out under the Ross Ice Shelf and found a hole that was only 1.2 meters in diameter.
I've seen the videos. It's pretty
locked onto a target, right, and comes back to the surface, right? Yeah. So and you can do this much better when you don't have water in the way, right? If you can use radar or lidar, right, and machine vision, this is a slam dunk. Okay, it's just and unless you have an errant thruster in that final stage docking, right, you're going to be way better than a pilot, right? So what do you do for a Europa mission? You use a couple of Falcon Heavies to put the pieces up, including the fuel, and they auto dock and auto assemble in orbit.
Or perhaps in the not too distant future, a Starship. I mean,
yeah, I'm not sold on Starship. Okay,
all right.
Yeah, you know, they've done some fantastic stuff, especially with their first stage boosters, you know, being recovered.
Yeah,
hats off, beautiful. But the fact is, the Falcon Heavy can lift roughly 75 tons, okay, to orbit, right? Well, here's the problem with Europa, okay? Mars is a piece of cake. You can put tons on Mars, right? Why is it easy? Because you can use aerobraking, right? You can't do that on Europa, right? There is no atmosphere. So when you come in there, and one of the reasons why they're doing this flyby mission with Clipper is because it is so expensive to even do things like go into orbit. You have to carry all that fuel with you to do your delta V braking maneuver just to get into orbit. Well, it's even more delta V to get something on the surface. And so it turned out that with the SLS, whatever it was, block 3, they calculated that you could only put 1 ton on the surface of Europa maximum. And that included anything like power systems, the lander, right? Everything, right? And your Cryobot had to be down there in the sub 200 kilogram range. Well, that's not a lot to work with, especially when it has to have its own nuclear reactor, you know, on board. So this is where you're getting into a logistics game. Well, you can break that by building a bigger vehicle in orbit in pieces. So maybe you do 2 or 3 Falcon Heavies, you assemble it in orbit, and now you have the ability to land significant mass on Europa. And of course, the more mass you have, what that equates to is reliability and performance capability. So I can now put redundant, you know, systems in. I can put bigger power supplies in. You know, I can put redundant communications elements in.
Falcon Heavy, 2 or 3 launches, that would be something like $200 or $300 million.
Yeah, well, so it depends on who you talk to, but 90 million a launch. So you're talking about 300 million. So my guess is that's part of it. Okay.
Yeah.
The development of the hardware, honestly, way less than 500 million.
Okay.
So well under $1 billion to do this mission privately, and maybe even 2/3 or half of that.
Wow.
Right.
Yeah, that's crazy. I mean,
roughly 1/10 or 1/20 of what the government could do it for.
Yeah, that doesn't really surprise me, but it's still an incredible figure. So if I came to you and told you I want to buy a Cryobot with its own power supply and everything, and I want to put it on my lander or whatever, how much would that cost?
You know, with space flight qualification, you know, this is where you have to play this game, right? It's like there are certain places where you can improve your reliability, not through gold plating single string thing. You know, if you go back and look at the Apollo mission and the lander, there were single string failure scenarios throughout that mission. So what did they do? They tested it forever, right? and they had this one thing and they crossed their fingers and said, okay, it's going to work, right? The way to get around that is you use redundancy of components, right? Well, I mean, I learned this personally long ago. I design closed cycle life support equipment. If you're a diver, you may know about rebreathers and things like that. You know, we designed the first commercial rebreathers back in the early 1980s. And because we were using them for cave diving and we didn't want to die, the question was, how do you put these together in a way that will be survivable? And we didn't want to go and build a gold-plated thing. We said, well, we need to be practical here. So we built redundant systems. We had parallel rebreathers. We had parallel gas supplies where you could cross-link those between rebreathers. Well, that same type of concept can be extended to space propulsion, right? And the classic example of this today is a Falcon 9. Go look at the back end of a Falcon 9, right? The reason it says 9 is because it has 9 thrusters, right? And that idea of cheap commonality, reuse of elements makes things more economical and way more reliable, right?
Absolutely, yeah.
So that's where you start thinking, all right, what do you need to make more reliable? And so it's one of these things where it's a game between, you want to be sure you don't fail because you might not get another chance, right? You know, if I were playing an expedition game, well, it's not a one shot. It's always, we're going back no matter what. You know, if you look at the kind of work we've done at Cueva Cheve in southern Mexico, my God, you know, I'm up to like 20 expeditions there now, right? And about 5 years of my life, you know, on site. So you use the information from the previous expedition to plan the next one, right? So the likelihood of a billionaire coming in saying, all right, we are going to find life no matter what, I will fund 3 or 5 missions, you know, that's a lot of money. And that would be a hell of a commitment, but it would be bold as heck, right? And the likelihood of success would be dependent only at that point on whether in fact there were microbes or something in, you know, the sub-ice cap ocean of Europa or Enceladus or Titan. You know, Titan is another one of these things where people don't really realize that the geophysical data indicate that there is a subsurface ocean there as well, right? Everybody's enamored by the superficial, you know, cryogenic, you know, hydrocarbon lakes. Right. You know, very, very intriguing, but, you know, 100 kilometers below that is this big ocean, right? And who knows what the hell is in there. It doesn't have quite the same tidal dynamics as Europa has. And that's why I would give Europa the better shot, I think.
Absolutely, yeah.
Because if you look at what drives microbes, there's 2 things. Number one, they have to have some type of chemical driver, okay, an electron donor and an electron receptor. Absolutely. Right? And typically that will happen at a place where there is geothermal energy, and that can be driven by tidal flexing of the, you know, internal crust of Europa by the orbit about Europa. So it is fairly unique. And if I had to say, you know, of all the ocean worlds, you know, you've seen the little map that Kevin Hand put out, you know, that's the one that you want to go to if you really want to do it. So, you know, if a billionaire came to me and says, by God, let's go do it, I would say, all right, plan for more than 1 mission. And the first one is going to be a test case. We're going to learn a lot. We're going to try to build it as reliably as we can. We're going to land. We're going to get through the ice cap. We're going to get as far into the ocean as we can. And then we take the data and try to figure out what the next move is. If we're super lucky, we find nanobacteria, this, you know, not long after we break through into the ocean. It's just swirling around there in the current, right? If we're not so lucky, well, then you have to get to the next phase, which is, okay, can we get a small enough nuclear powered AUV to go out and extend the radius to start trying to find those hydrothermal vents?
So that currently it isn't possible. The small AUV with an
no, it is possible. It just means you have to design it, right? And right now, just to give you an idea, sunfish would have to be reduced in size, probably on the order of, I would say, 40% to be able to fit it into Thor. Right, we would have to change the exterior geometry to make it fit into a tube, and then you have these issues. All right, how are you going to deploy it? Sure. Is it going to come back and how does it communicate, all of these little things. So it turns out if you don't have to retrieve it, then things are a lot easier. Deploying is a lot easier than retrieving.
Sure, yeah.
You know, and so for testing these, you know, Antarctica is the classic test case. In fact, I don't know if you're familiar with the term decadal survey.
Yeah, absolutely.
Yeah, so NASA is just finishing the next big one, and we put in a white paper, several actually, a white paper, but I was the lead on this one to establish a permanent test base in Antarctica for proving out these concepts of cryobots and sub-ice AUVs for the purpose of detection of life. And there are enough interesting targets in Antarctica where, you know, if you could prove it there, you've got a darn good chance of proving it on Europa.
We'll see what the Decadal survey says when it comes out in, I don't know, March, something like this, next year.
Sometime in that time frame, you know. And the problem with it, of course, if you're familiar with NASA, is it's a tribal warfare situation. You know, the Mars tribe is very powerful.
Yeah, I've read the book on the Europa Clipper mission. It's a bit infuriating sometimes to see.
Have you read Kevin Hand's book?
Yep. Yeah, I have.
Yeah. Okay. Oh, you're very
I was surprised that he, because he's a very measured scientist. So, you know, when he's in public, he doesn't say, you know, there could be multicellular life on Europa. And yet in his book, he's saying that, well, technically it could happen. So it's interesting. But it's a great book. I would love to have him.
Well, he's the guy to follow
Sure.
at JPL for certain.
Yeah.
None of the other people have the guts to try to push for what he's trying to do.
Yeah.
You know, it can be politically dangerous to do that, you know,
Sure.
because, you know, it is this tribal situation, sadly. And once they make a decision to go with one, well, because it costs so much in the government, you know, he might never be able to get his funded because somebody decided to do a Titan mission instead.
Sure.
You know, it's just that way. However, you know, he's a very good friend, by the way. And both of us have come to the conclusion that the alternative path, by getting a billionaire to fund a mission, is not only feasible, it is perhaps the most likely way that it'll happen within the next 50 years.
Sure. Yeah. So you need someone who says, you know, I have bought launch vehicles. Here's $300 million, $500 million, and let's roll.
Yeah. No, if you said to me, come up with a real budget, I have the money.
Yeah.
I could hone it down to even better, right? It would really be dominated by the launch cost, the actual development.
Yeah, that's what I'm trying to have some hard numbers on, because I'm really curious how cheap.
Yeah, I would say certainly within the $500 to $700 million range if somebody put the money on the table today. Okay. And a large part of that would go into the design, the validation of the safety issues of the reactor. And into the radiation hardening of all of the electronics to make sure that you know, galactic cosmic radiation was not going to cause our, you know, life detection circuitry to go out and things of that nature. You know, during thermal vacuum testing, these are all logical things that you do have to do if you want them to be you know, reliable.
Absolutely.
And the other thing is that within that, you would have to build a large scale version of what we have right now, which is a cryogenic test tank.
Chamber,
yeah, a big one that has probably on the order of 20 to 30 meters of ice column. The reason is you have to be able to test the full size vehicle, and we've done thermal simulations, and it turns out that the length of such a facility has to be on the order of at least 3 vehicle lengths, and the diameter has to be on the order of 10 minimum diameters of radius. So if the vehicle is 1 meter in diameter, you need 10 meters of radius to prevent boundary condition affecting the results, right? But once you have that, you know, you could then go in there and put an actual nuclear reactor and fire it up and make sure that things are working.
Yeah, that's incredibly cheap. I mean,
if you'd asked me 10 years ago, I would have said, nah, you know, it's going to be a long time. It's going to be 2050. But now No, I mean, after all the stuff that we've done so far, we're on track. I can see it. I would say that right now, there is nobody on this planet that is closer than we are with building real hardware.
That's for sure. Yeah.
to do that mission. And I see it laid out. I see the path.
It's amazing. Yeah. And so I think we've done an hour. So, I mean, perhaps I should wrap this up. So again, thank you so much for doing this. That was
my pleasure. If you have any other questions, you can email me or whatever, and I can let you know what's happening from time to time. But
that would be great.
Right now, things are interesting.
Absolutely, yeah. I mean, I'm blown away by the price tag on such a mission. So, Dr. Stone, thank you so much again for joining me, and I hope we get to catch up a little bit later.
Very good. My pleasure. Thank you.
Thank you so much.
All right. Bye-bye.
Bye-bye.